Telemetry drops before closest approach is even complete, and the comet is already punching the spacecraft harder than the model allows. Giotto's camera feed turns into a crawling storm of static as Halley's comet fills the frame, darker than any simulation had prepared us for. Every few seconds, the signal snaps, like something is physically hitting the link itself. In the control room, we are watching a live feed that should not survive this level of impact. Dust is not a background detail here, it is a physical barrage, and the antenna lock begins to drift under repeated strikes. The visual anchor appears. A grainy, static, heavy transmission. A dark nucleus swelling in frame. Streaks of interference slicing across the image like scratches on glass. Then, a sudden misalignment in telemetry. The spacecraft is still transmitting, but not in agreement with itself. We log the first warning as a routine degradation. But the signal does not recover. It fractures. Every correction we send back through the uplink arrives inside a worsening noise field. And that is the first problem. The environment is not passive. It is actively rewriting our communication path in real time. Within minutes, the dust density spikes beyond predicted thresholds. Hypervelocity impacts begin to register not as single events, but as continuous pressure on the system. The camera does not go blind all at once. It is taken apart, frame by frame. Then the second layer fails. Attitude stability. The spacecraft starts to wobble under asymmetric impacts, tiny nudges accumulating into a slow loss of lock. The image of the comet grows larger, then unstable, then fragmented. The visual anchor returns, but now the static is thicker. The nucleus is still there, but harder to trust with every frame. Mission control shifts from monitoring to correction. We fire stabilization commands. We tighten the pointing solution. We compensate for drift. Each correction works for seconds, then fails harder than before. The system is not stabilizing. It is absorbing our solutions and turning them into new errors. And that is where the failure cascade begins to show its structure. The spacecraft was not built for this density of particulate impact. Our models assumed sparse dust, predictable spacing, clean flyby geometry. But Halley's comet is not sparse. It is saturated. Every meter closer adds more collisions per second than the last. The visual anchor returns again. The same grainy comet nucleus. But now, the image tears diagonally as if the camera itself is being dragged sideways. One controller calls out a concern we all already see. The signal is no longer continuous. It is stitched together from surviving fragments. We attempt to isolate the antenna lock, recalibrate pointing, rebalance thermal drift. Each system correction holds briefly, then collapses under a new impact pattern. The spacecraft is not failing in one place. It is failing everywhere at once, in different rhythms. But the next image removes the safest explanation. Telemetry does not just degrade, it misaligns. Time tags drift apart. Data packets arrive out of sequence. We are no longer looking at a single stream. We are reconstructing reality from broken pieces that no longer agree on when they happened. At this point, the mission stops behaving like a flyby. It behaves like a survival event. The visual anchor appears again. Now the comet fills nearly the entire frame. The nucleus is partially obscured by streaking debris. But something worse is visible. The pattern of interference is directional, not random, not noise. It looks like a sustained environment of impact flow. And that changes everything. Because if the impacts are directional and continuous, then the spacecraft is not passing through a cloud. It is crossing a structure, a dense inner coma layer that behaves less like dust and more like a kinetic barrier. Midway through the pass, we realize the second failure is not independent. It is caused by the first. Camera degradation reduces tracking accuracy. Tracking loss increases antenna misalignment. Antenna misalignment reduces data recovery. Data loss delays correction timing, and each delay increases exposure to the next wave of impacts. A full cascade loop. We try to break it, shift to redundancy channels, force backup orientation logic, but redundancy systems are already compromised. The same impacts that blind the primary camera are now corrupting secondary sensor stability. The visual anchor returns again. This time, the comet is barely visible through interference bands. The image is still there, but it no longer behaves like an image. It behaves like a contested signal. Then the midpoint shock arrives. Impact density spikes beyond anything in pre-mission estimates. Not gradually, suddenly. A threshold is crossed, and the spacecraft enters a regime where every second includes multiple high-energy particle strikes on exposed surfaces. The antenna begins to lose stable Earth lock entirely. We are no longer commanding a spacecraft. We are listening for it between interruptions. The cascade deepens. Power fluctuations appear as the solar array takes uneven dust hits. Thermal readings jump. Orientation thrusters fire more often, trying to correct a body that is no longer reacting predictably. Every correction introduces new drift. And still, the comet grows in the frame. The visual anchor returns, but now it is unstable in a different way. The nucleus is no longer centered. It slides across the field of view as if the spacecraft is being physically shoved off axis. The static is not just noise, it is impact history being written in real time. We attempt emergency stabilization protocols, narrow the data stream, prioritize antenna pointing over imaging, sacrifice camera clarity to save communication. It does not hold. The antenna finally breaks stable Earth lock. Not fully lost, but intermittent, flickering. A conversation that only arrives in fragments. And that is where the real failure begins. Because now we are rebuilding the mission from incomplete memory, from partial transmissions, from fading static that no longer represents a single continuous reality. The visual anchor appears again. This time, it is almost gone. The comet is a shadow inside noise, but the shadow is still moving, still growing, still passing through us faster than expected. Every assumption about comet safety collapses into a single operational truth. We are inside the impact environment, not observing it. The spacecraft is not imaging Halley's comet. It is surviving it. The cascade reaches its final stage when antenna lock returns briefly, just long enough to transmit degraded images. And in those images, the nucleus is surrounded by constant streaking impacts that never pause. No gaps, no calm interval, only continuous collision. That is when the consequence becomes irreversible. The spacecraft cannot fully recover stable orientation before exit. It has already lost too much control authority to cumulative damage. Each subsystem is still functioning, but no longer coordinating as a single system. We are receiving fragments of a mission that has already passed through its most violent region. The visual anchor appears one last time. The comet shrinking slowly now, but the image is still unstable. Not because the comet has changed, because the spacecraft that captured it can no longer hold a stable view of anything. And that is the final realization. Halley's comet did not overwhelm the mission with a single impact. It dismantled it through continuous, layered failure. Each system we trusted became the reason the next system broke faster. As the signal fades into a thinning stream of static, we understand what the early models missed. This was never a flyby with imaging. It was a collision environment with brief moments of visibility. And the last usable frame is not an image of the comet. It is proof that the spacecraft stopped being a camera long before we stopped receiving it. We did not lose Giotto in space. We lost it inside the data it was still trying to send. The signal ends like it began, inside the storm.